This lesson is about using bond energies to calculate enthalpies of reaction. And there are equations out there that you can use to solve for bond energies, but it'll seem a little bit contradictory to an enthalpies of formation equation. It might result in some confusion. It's not that it is contradictory, but it seems to be that way for many students. So rather than learn an equation to do bond energies, I'm going to use this logical approach, just a few basic things you need to understand, and it makes the process considerably simplified. You don't need an equation in order to solve. So what I'm going to do here, I'm going to do the enthalpy for the reaction of the combustion of methane. So methane reacts with oxygen. First thing, I'm going to predict the products, carbon dioxide and water. And then I'm going to go ahead and I'm going to balance that in the way I would do on most thermochemical equations in order to have an enthalpy of reaction that's equal to an enthalpy of combustion. I'm going to balance with a coefficient of 1. Even if I end up with a 0.5 or a half or whatever, I'm still going to leave that coefficient for the hydrocarbon as a 1. So in order to balance that, I need 1 CO2. I need 2 H2Os. And then that's going to leave me with 2 O2. So the ratio there is 1, 2, 1, 2. And down here at the bottom, I've got some different bond energies given. And the important thing here to note in order to do this process is what has to happen to break a chemical bond. So I'm using the Legos here to represent my methane and my oxygen. And in order for me to make these products, I've got to make an investment. I have to put in some energy to break these apart. So as I go through this process, I need to understand what it takes to separate two atoms in order for us to put them back together once we get over to the product side. The other thing here that I have to account for is the fact that there's stoichiometry, there's coefficients, it's 1 to 2. So I don't have enough O2 here, so I'm going to bring in another diatomic oxygen so I can represent here what's going to take place. So there are problems where you don't have to break everything apart, especially if it's an organic molecule and we're just changing a functional group around or something like that. There are some shortcuts, but I'm going to go ahead and show you the process of breaking everything apart, simplifying the mathematics. So to do this, I'm going to start with my CH4, and I'm going to remove one of my hydrogens from that. And that takes an investment on my part of positive 413 kilojoules. Positive because I'm physically inputting the energy to cause that separation. And then I'm going to do it again. That's another positive 413. And again. And one final time. So now I've completely separated that methane out into a carbon, 4 hydrogens. I've broken all those bonds, and it takes 4 times 413 kilojoules to do that. Again, 4 because there are 4 hydrogens bonded to the carbon. The oxygen is a little bit different in terms of what's going to happen here mathematically. It takes me an investment here of 495 to separate it, which does completely separate that diatomic oxygen molecule, but I also have to account for the coefficient here of 2. So I've got to do that again because there's another O2 molecule that I'm going to break apart, and again that sign is going to be positive. I'm inputting energy to make that happen. On the other side here, we're ready just to put these things back together. So I've got my hydrogens, I've got my carbon, and I've got my oxygens all set over here, and I'm ready to start putting these things back together. The important thing here to note is all of these energies are required to be input to break it apart, which means when I get to the product side of the reaction, the sign's going to change. I'm going to get energy released on that product side. So I'm going to start with the carbon, and I'm going to place 2 oxygen on that carbon. So I'm going to place 1. All right, now I find my carbon-oxygen double bond. That's going to be negative 799. And then I'm going to place another one, and that's another negative 799. And again, that's 799 twice because that's 2 carbon-oxygen double bonds in one of those molecules. All right, so now I'm ready to start through with the H2O. I'm going to place a hydrogen on the oxygen. That's negative 463. And then I'm going to do it again. And that's another negative 463. And I know if you're really good with mathematics, you probably understand you could shortcut the last part of this, but I'm going to go ahead and take it through in baby steps just to simplify the process. And another negative 463. And again, another negative 463. So again, it's twice for each molecule because there's 2 hydrogen on each one bonded to an oxygen, and then it's repeat the process again because we end up with 2 H2O molecules when we're done. All right, so the next step here is to start working with these numbers, and again, mathematically there are some shortcuts you can take, but I'm trying to do everything here with just simple addition. When I add up 413 4 times plus 495, I end up with a total here of positive 2642, and I could go right ahead and start subtracting off all the other side, but I'm going to go ahead and do those separately so I can double check my work. All right, yep, positive 2642, and then on the product side, I end up, when I add up all those numbers, with negative 3450. And all I'm going to do is I'm just adding these up. There's no fancy equation. I'm just remembering that on the reactant side, it's an input of energy to break a chemical bond. I have to make that investment, which means on the product side, I get a return. I get energy released on the product side, and in order to solve, I'm simply just adding up all of the numbers that I have here. I did go ahead and do them in 2 separate halves. I did reactants and products. Again, be very, very careful with the negative signs. It's easy to make a mistake there. I end up with 2642 plus a negative 3450, which gives me a delta H of this reaction equal to negative 808 kilojoules. That also could be called an enthalpy of combustion for a mole of methane as well. And as I would expect on this, I end up with a negative value, which from your other studies in thermochemistry, you should realize that is exothermic, and it is a combustion process, so exo energy is released.